Hi Jake, just marking your paper here, and looks like I've got the same marks as you. Right, so we'll assume we're both right on all this page. Yeah, they're the same as me anyway. Okay, however, on this question here, we have a difference. I'm the same as you on B, but for G, I've got a different product. This is what I've got for G. I've got the skeletal backbone there with a bromine on one end and a bromine on the other end. The reason why I've gone for this is that in the question it says that unusually, or rather in contrast to the other members of the same class of compounds, right, B here reacts with bromine in the absence of light, right? So that means it's not free radical substitution. Free radical substitution needs light to make a couple of free radicals out of the bromine. Also, it says F and G are isomers, and if you look at your previous page as to what F is, this would be an isomer of F. All right, so that's what I've got for G. So moving on to part D, I think this is good, and this 152.1 is the same as what I got for formation of A, and formation of B 185.1. Yeah, that's what I got too. Well done. So I got minus 33 as well. So that's good, but my explanation is different. So see where it says comment on what you obtain. So I don't know whether the comment's worth 1 or 2. I suspect 2. And what I think is that A is more stable than B despite the pi bond. Okay, so B's got a pi bond. I guess you've done pi bonds, have you? If not, so you've got carbon here and a carbon here, and you've got a sigma bond here, and then you've got your pi orbitals that overlap, and this becomes the bond, the overlapping part of the orbitals where the electrons spend most times becomes the pi bond. So that is a weaker bond than a sigma bond. Okay, so so despite that, A is still more stable. Why? I think there's a concept called, well, I know there's a concept called ring strain, but I think that applies here. So if you've got a molecule like this, where the angle between our carbon-carbon bonds is 60 degrees, that's quite a small angle, isn't it? Whereas in the other one, which whatever the letter it is, it's a tetrahedral structure, isn't it? So you know you're going to have some sort of tetrahedral structure like that, where the bond angle is 109.5. Yeah, so that going back to this one here, you've got, or rather, if you can't see my cursor, going back to the triangle-shaped molecule, 60 degrees in between the sigma bonds of the carbons, and that's a small angle, which means that you're going to get ring strain, which weakens the molecule because there's more repulsion there between those bonding pairs. So that would be how I would explain it, in fewer words than that, preferably. In part E, I've got a different explanation. Mine's a bit simpler. I hope that doesn't mean it's too simple and incorrect. So just talking through what I was thinking along the lines along which I was thinking was when in this molecule here, our triangle molecule, essentially we've got 3 CH2 groups, right, and our enthalpy, is it enthalpy of combustion? Our enthalpy of combustion is 2091. As in the early part of the question, and if we've got 3 CH2 groups, right, that is minus 697 per CH group, per CH2. Whereas in our, is it cyclohexene? In our cyclohexene, the molecule we're comparing with, let me draw it up here. Yeah. In our cyclohexane, we have 6 CH2 groups. Right, so 6 CH2 groups there, and it gives us combustion minus 3920. Alright, so minus 3920, but divided by 6 this time, equals minus 653, I think, per CH2 group. Okay, so we're comparing our minus 653 to our minus 697. So the comment is that less energy is required to break the first carbon-carbon bond in our triangular molecule because of the bond strain that we were talking about before. Therefore, the enthalpy of combustion is more exothermic because we've got less bond breaking endothermic process. Whereas in our hexagonal molecule, cyclohexane, there is less bond strain, right? So the bond breaking is more endothermic, right? And hence our combustion enthalpy is less exothermic. So that would be my personal answer to E. So move on. Now I think I'm missing a page. The first part of question 4, but it's quite straightforward, I think. So if you're referring to your answer machine, answer book, and you're looking at question 4, part A, +3 obviously for arsenic for part A1. Part A2, I trust you got that right. I'm not going to read that equation out. Part B, 1. I wonder if you know that term, same environment. It's a term that comes up in NMR, which we've not studied yet. So if you look up NMR, you'll see what it means by environment. There'll be a lesson on it in the textbook, but it just means that you know, it's all of the bonds are going to be the same. All of the electron withdrawal or donation induction effects are going to be the same. So that the geometry of the shape I've got as tetrahedral with arsenic in the middle and 3 OH groups coming off the arsenic. Arsenic's in group 5, of course, so you're sort of looking at it like an ammonia molecule, because it's going to be a lone pair there as well, I guess. All right. And then the equation, which I suspect you didn't have the same as me because of your next answer, but I've got 1 mole of arsenic oxide plus 3 moles of water gives 2 moles of the acid. What's the acid called? Arsenic? No. Arsenous acid. Yeah, 2 moles of arsenous acid. Okay, so that leads us on to this part 3 answer here, and I've got a number that's twice this because my moles of arsenous acid were 2 moles of the oxide, so I multiplied that up by 2. So you might just check that. Okay, moving on. Yeah, I guess this is right. I've got 2.06 times 10 to the minus 27 grams. If that's what this next bit says, that's good. yeah, looking at part 2 here, I've got the same answer almost. I have a factor of 18 there, which might be my mistake. I didn't, but if you want to go through that and see whether 15's right or 18's right, you're welcome. Could be my mistake, I don't know. I'm just looking over my answers. When I converted meters cubed into kilometers cubed, I divided that by 1,000,000. So if we'll imagine a cube, which is 1 kilometer, yeah, or 1,000 meters. So 1 kilometer is 1 cubic kilometer is equivalent to 1,000,000 cubic meters. 1,000 times 1,000 times 1,000. So I think that might be where we get a different number, 15 versus 18. Okay, there's a couple of differences for part 3 here. The first one is it's talking about atoms of arsenic, and this concentration I think is for the arsenic oxide. So you're going to have to multiply this by 2 because it's As2O3. So then instead of this number, I got 1.252 times 10 to the 23. And then this little calculation is the same one as I did, except I had 1 times 10 to the 60 up here. I can't remember why. I had a quick look through the question and I couldn't see why I would do that, but maybe that'll help, maybe it won't. In which case we get a number instead of this number. We get 8 times 10 to the 36. 8.00 times 10 to the 36 decimeters cubed. And therefore the number of bottles is just going to be that volume there divided by the volume of your bottle, which is 0.028 decimeters cubed. Alright, because I've just converted this into decimeters cubed, which is this number here, and so my answer comes out at some crazy number of bottles, 2.85 times 10 to the 38. Alright, which I've got no idea whether that's right or wrong, to be honest. It's such a crazy number. Anyway, if you want to go over it again and see if the second part of this question, see if I'm right, that's a good thing to do. Then all the acid stuff is pretty straightforward, I think, and it's all correct. So hopefully, Jake, that's helped. Cheers.